In everyday life, we can identify objects' material composition based on the thermal cues. For example, a metal bottle feels cooler than a plastic bottle. The wooden door feels warmer than the metallic door handle. However, it is still challenging to perceive objects' material in VR. We present ThermAirGlove, a pneumatic glove which provides concurrent on-hand thermal and force feedback through embedded air bags and external control systems. ThermAirGlove could generate the thermal cues of different materials, and support users' material discrimination and identification in VR. In ThermAirGlove, the thermal feedback was achieved by controlling the temperature of the air pumped into the airbags, and the force feedback was generated by controlling the volume of the air. ThermAirGlove consists of a glove with 5 inflatable air bags on the fingers and a thermocouple installed in the middle finger airbag. The thermocouple will sense the airbag temperature in real time, and provide feedback for the temperature control. We also developed 2 temperature chambers, one hot and one cold, using the Peltier modules, and a pneumatic and temperature control system with an external power supply. This is the system diagram of ThermAirGlove. When the user wears ThermAirGlove with empty hands in VR, the Pump 2 will deflate the airbags. When touching or grasping different materials in VR, the system will control Pump 1, Pump 3 and Pump 4 to mix the hot, the cold, and the room temperature air, to achieve different temperatures in the airbags and control the thermal feedback. We calculated the values based on the semi-infinite body model of human skin contacting with different materials, and fit the airbag temperature with these predicted curves using PID control. Our technical experiments showed that the pneumatic thermal control system can generate the real-time temperature following the thermal trend predicted by the theoretical models, for users grasping virtual objects in different materials, such as copper, foam, and glass. We conducted 2 user perception experiments to investigate users' perceived intensity of the generated thermal stimuli, and their capability of performing material identification with ThermAirGlove. We assumed the skin temperature as 34 degrees and then measured the step responses of different temperature change, including 2 directions, cooling and warming, 2 rate of change, 1 degree per second and 2 degree per second, and 2, 4 and 6 degree 3 intensities. We conducted user perception experiment to measure participants' subjective ratings of thermal intensity. The results showed that the cooling processing was rated significantly more intensive than warming, and significant differences in the intensity rating between 2 and 4 degree, and 2 and 6 degree. The fast rate of change was rated significantly more intensive than slow rate. Besides, we performed a k-means clustering processing to categorize the 13 stimuli. The results suggested that ThermAirGlove could generate 5 different levels of stimuli that can be distinguished by users, and post-hoc pairwise comparison showed significant difference in the intensity ratings between all clusters. Then we adopted user perception experiment for material identification among copper, glass and foam 3 materials. In this study, 2 types of stimuli, real and ThermAirGlove, were presented to the participants in 2 sequential sub-sessions in a counterbalanced order. The results showed that ThermAirGlove could support users' material identification, with no significant difference compared to perceiving the real physical objects. Finally, we conduct a set of user studies to investigate VR experience with ThermAirGlove. We compared 3 modes of objects manipulation, using the bare hands without ThermAirGlove, wearing ThermAirGlove with inflating the room temperature air only, wearing ThermAirGlove with thermal feedback for temperature and material simulation. The results showed that using ThermAirGlove in immersive VR could significantly improve users' experience of presence compared to the current commercial VR settings. Before the end of the video, we show some VR application examples of ThermAirGlove.